Hello and welcome. In this lecture, I'll be discussing about photoelectric effect. This is part first of my lecture in this video. Now, what is photoelectric effect? Photoelectric effect is a phenomena in which light in the blue or ultraviolet region, when it falls on a metal plate, then pseudo-moving electrons are emitted from its surface. This phenomena is known as photoelectric effect. And the electrons which are being emitted from the surface, they are called photoelectrons. The photoelectrons can be obtained from non-metals and gases as well. Now, most metallic surfaces show photoelectric effect with ultraviolet light. But it has been seen that in alkali metals, for example, lithium, sodium, and potassium, the photoelectric effect can be seen with visible light. Photoelectric effect has originally been discovered by Heinrich Hertz back in 1887 when he was doing experiments with radio waves. He had two electrodes with him which were maintained at very high potential. And the spark would move from negative electrode to the positive electrode. And when he shone the ultraviolet light on the negative electrode, then the spark would move to a further distance. It was Hallwig's, and Hallwig's just after 1 year, he showed that when ultraviolet light was shown on the negative electrode, it was actually the emission of electrons from the negative, this electrode, which would help the spark to jump further. Photoelectric effect has been this is animation here, and in this animation we can see that electrons are emitted when the light falls on the cathode, and these electrons reach the anode and they come back to the battery. Now, this photoelectric effect has been studied by many scientists, for example, J.J. Thomson, Leonard, Richardson, Compton. They did a series of experiments to study the relationship between photoelectric current, intensity of light, kinetic energy of these electrons, and their dependence on the wavelength or frequency. Now, Philip Leonard, he established an experimental setup to study the photoelectric effect back in 1902. And he demonstrated that these charged particles which were liberated from the cathode, they were identical to electrons which were discovered just some years back by Thomson in 1897. Now, the experimental setup of Philip Leonard, it consists of an evacuated glass tube with a cortex window here, and this cortex window would allow the ultraviolet light to pass through it, and that light would fall on the cathode C. These cathode and C were fitted on it, and then there was an external circuit, a commutator, which would change the polarity of the battery, then micro ammeter and a voltmeter, a rheostat, and a cell. In this experiment, we have actually three variables which we would study, and then we will draw conclusions from it. The first variable is the voltage between cathode and anode. The anode is maintained at positive potential, it is maintained at negative potential, and it is maintained at zero potential, because we are studying different aspects of this experiment. Now, when we put the anode at positive potential, then electrons which were which were coming from the cathode, they would be attracted towards the anode, and they would slowly move, and therefore when the electrons move from cathode to anode, it was a completely space earlier. Then a circuit is complete, the current flows in the circuit. So this was one part. Now, when it was given negative potential, negative voltage, then it would repel the electrons back. Only those electrons which had the very high kinetic energy, they would be able to reach from cathode to anode. And it depends upon the voltage as well on the anode. Then the second variable is the intensity, which we study. The intensity is actually the number of photons or number of particles per unit area and per unit time which falls on a surface. And this intensity we can visualize by this thing, that if we have two bulbs, one is of 50 watt and other bulb is of 100 watt, then 100 watt bulb would be twice having 2 times intensity, more intensity than the first one, 2 times more intense. It will give more photons per unit area, per unit time. Then frequency, it is actually the energy of these photons, and it is inversely proportional to the wavelength of the light. Now we'll study the graph and other things. Now see, we have a view of a small part of this experiment here, a tube. Now here, if we place a filter here, suppose a green filter, and this green filter would allow only green light to pass through it when we put a white light source here. And this white light source, when we put, it has its intensity can be changed. For example, it is a bulb which gives light of different intensities. For example, it is suppose 25 watt bulb intensity, then 50 watt, then 90 watt, then 120, etc. And we have a varying intensity. But before that, we have to make the circuit operative, so that when the light falls on it, green light falls on it, it conducts the electricity. The electrons are emitted from the cathode and they reach the anode. Anode is maintained at some potential. Now, when the intensity is suppose 25 watt, then we measure the current in the circuit. Now we change the intensity to 50 watt, we again measure the current. And then we change it to suppose 90 watt, we again measure the current. Then 120 watt, we again measure the current. Then we plot a graph between photoelectric current and the intensity. It is a straight line. It shows that the intensity of light or intensity of these photons which fall on the cathode, it is proportional to the current. It is proportional to the current, and therefore we have established the first law of photoelectric effect. What is that? The number of electrons emitted per second varies directly as intensity of incident light. Now it is directly proportional to the number of electrons which come from the cathode. They are directly in proportional to the photons which strike the cathode. Now this is experiment number first. Then we study the experiment number 2. In the second experiment, we again maintain this circuit at some anode at some potential, and then we allow the light of some intensity, suppose I1, to fall on the cathode, then current flows. Now suppose anode is at a zero potential, and ammeter shows a deflection, and there's some current flowing through it. Now if we give slight positive potential to the anode, then current starts increasing, and then it goes in the saturation stage. Saturation stage means all the electrons which are available at the cathode, they are able to reach to the anode. All the electrons reach to the anode. And then when we have obtained this curve, we again go back to the point 0. And at this point now, the anode potential, we are decreasing. We are moving now to we are giving negative potential, negative voltage to the anode. Now here, when you are giving negative potential to the anode, it will repel these electrons. Now the electrons only with high kinetic energy will be able to reach the anode. Those which have less kinetic energy, they will not be reaching to the anode. Consequently, the current starts decreasing, and when this current starts decreasing continuously, and we are increasing the anode negative voltage, and a point reaches where all the electrons are being repelled. They are not now reaching to the anode, and the current completely stops. And at this point, this becomes a stopping potential. The current becomes zero. Current becomes zero. Now, if we increase the intensity of light, we now use 50-watt bulb, and again repeat the experiment in the same way, we'll find that the stopping potential will remain the same. And again, we are using the same light. For example, green light we have started, we are using the green light with the intensity we are increasing. And in the third case here, suppose we are using 90 or 120 watt green light, and again we are repeating the experiment. The stopping potential will remain the same. Now, what this means actually, the stopping potential is actually the measure of the maximum kinetic energy of electrons. Because when you give the high negative voltage to the anode and current completely starts, these electrons completely stop moving from cathode to anode. That means the maximum kinetic energy of these electrons, it has completely been annulled by the negative voltage of the anode. That means the stopping potential is a measure of kinetic energy. And this is independent. This kinetic energy or the stopping potential, it is independent of the intensity of light. It is independent of the intensity. This becomes the second law of photoelectric effect. This is maximum kinetic energy of photoelectrons is independent of the intensity of light. It's very important. Now we'll move back. Now experiment 3. Experiment 3 is when the incident light, suppose you are maintaining now some watt of this light on the window. Suppose 25 watt green light you are maintaining. Then again you are repeating the experiment, and it is stopping potential is V01. It is V01 here with some frequency mu1. It is the frequency of the green light which we are actually using. Now we move back with the same intensity, but we are replacing the light by a blue light now. Now blue light has got a greater frequency. Now when we are using it, now we again repeat the experiment. Now in the second case, you will see you have to apply higher this stopping potential so that the current becomes zero and the curve becomes like this. And in the third case, you are now using the violet or indigo light like this. And again, you are repeating the experiment, and again, you have to increase the stopping potential here so that current becomes zero. Now see, in this case, you will see that the stopping potential, it becomes directly proportional to the frequency, and it is independent of this intensity of light. Now, if we plot a graph between stopping potential, we have 3 readings for stopping potential and 3 frequencies. If we plot a graph between stopping potential like this and the frequency, it will be a straight line. And if we move backward, and here it touches the x-axis frequency line at this point, and this becomes a frequency nu zero, which is called the threshold frequency. And this threshold frequency is the frequency below which, that means below which lower than this the emission of photoelectrons is not possible. And now we are establishing 2 more laws of photoelectric effect. This is the maximum energy of photoelectrons increases linearly as the frequency of incident light. See here, V01 is directly proportional to V1, V02 is directly proportional to V2, V03 is directly proportional to V3. It's actually a straight line. And we see that it increases linearly as the frequency of the incident light. And then we also establish this law: the emission of photoelectrons cannot occur if the frequency of the incident light is below the certain value called threshold value, nu0. However strong the intensity of light may be, nu0 is different for different surfaces. Now, if we have a surface, different surface here, this cathode is different, then this threshold frequency will be different. And of course, that will be parallel to this straight line. And we have established these three laws. And in whole, we have seen that when the light is incident on the cathode, at the same time, the photoelectrons are emitted. And there is no time lag between the emission of electrons and the incidence of these photons. Now, these are the four laws. The fourth law becomes the photoelectrons are emitted almost instantaneously, however poor the intensity of incident light be. That is the time lag between the incidence of radiation and the emission of electron is 10 raised power minus 8 seconds. That means instantly it takes place. Now we'll be discussing further on this topic in our next video.